Hello, and welcome to the Future of Data Meetup group for Northern Virginia on Thursday, September 9th. Glad that you're here. My name is Michael Ridley, and I work in our technical marketing organization. I've been with Cloudera for, oh gosh, I don't know, 8.5 years, and I spent the first number of years at Cloudera working in our consulting organization, working with customers on architecture and technical implementation. And then for the last couple of years, I've worked in our technical marketing organization. Tonight's topic is accelerating AI training using Nvidia GPUs. And we are going to have several presenters, two presenters, that have put together presentations that are sort of complementary ways of using GPUs on different parts of the data analytics lifecycle. Tonight we are live streaming on LinkedIn, Twitter, and YouTube. And so again, if you're not quite sure where you are or how you got here, this is the Future of Data Meetup group on meetup.com for Northern Virginia. We are going to have an exciting raffle tonight. So the raffle rules. Everyone who participates in the chat will be entered into a drawing. So we want you to ask your questions early and often. You don't have to ask a question, just any interaction in the chat will get you entered into the raffle. So you could say hello, you could say what the weather is where you're from, you could say your favorite thing about Cloudera or CDP, or your favorite thing about Nvidia GPUs. Maybe you like the color, maybe you like the different manufacturers, maybe you're excited about the cooling systems, I don't know. Anyway, at the end of the meetup, we're going to have two winners, and they will win one of these fabulous prize packages that you can see on your screen. And so the random drawing will take place at the end of the presentation, and you must be present to win. So you actually do have to stick around throughout the content in order to be eligible to win the raffle prize. So I know people, come for the raffle, stay for the content. That's what we like to hear at Cloudera. So without any further ado, I will introduce our presenters for this evening. So they are going to be Nick Pelez. Hello, Nick.
Hello, how's it going?
Very well. And Jake. Hello, Jake.
Hey, how's it going?
It is going A-OK. So before we get into the exciting presentations that you both have prepared for us to learn all about how to use GPUs for accelerating workloads, Nick, if you could maybe justify why you're qualified to speak on this topic.
Sure. So I guess I'll give a little bit of background. I actually kind of started off my engineering career in the aerospace field. So I graduated with an aerospace engineering degree and kind of went into the analytics side. At first, I started some low-level programming, like I was basically making C#.NET applications to track and monitor fleets of military jet engines for the U.S. and kind of expanded my role into the analytics side. But I got to keep my programming side in the sense that I actually wrote all the code that parsed all the data that gave me results, and then I got to present that data to the squadron leaders and everything, and I got to be the guy that told them, hey, don't fly this plane, this is why, and had to back that up with data. And took that experience and came over to Cloudera, where I basically got to apply it with new cutting edge technology, which frankly before we were kind of stuck in a closed shell, right? There wasn't a lot of open source and like modern libraries that we could really implement.
Sure.
Whereas here, I get to see all the cool new stuff, and I get to play with it, and I get to show it to a bunch of other people. So it's been a good time.
Well, fantastic. And I know that our users benefit from hearing from people with sort of real world experience, where it's not just academic. And Jake, you're relatively new to Cloudera. Welcome to the Cloudera family. And I know you work in product marketing on our machine learning products. Do you want to give a quick bit about your background and what brings you to our meetup tonight?
Yeah, for sure. So I've been at Cloudera just about 5 months now, and I come by way of I was working at ExxonMobil before as a data scientist and then as a solution architect. So I actually worked pretty closely with Cloudera on a lot of the projects there. Originally, I worked on a lot of what we call upstream projects, where I was working on projects up in like the Alberta oil sands and trying to do some predictive modeling up there for bitumen loss. And then have transitioned more to that architecture role in the downstream. And so we are working with Cloudera on bringing together like data from all our refineries across the world. And always been kind of in the data space since I graduated, and really have always loved like working in data science, getting my hands dirty with the data, and being able to find unique new things. And one of my passions too has been big data, kind of as an application of that. So coming to Cloudera was a pretty natural extension for me. Yeah, and so now I work at Cloudera. I work as a technical product marketing manager, and really what I'm focused on is how can I demonstrate the cool new things that you can do with our machine learning tools. Specifically, I focus a lot on Cloudera machine learning. So yeah, that's why I'm here.
Well, fantastic. And as I said, we're going to have a presentation from both Nick and Jake. And I think what we're going to be able to learn as we look at their two presentations is which field is better at data analytics. Is it aerospace or is it oil and gas? And so because Nick is going to be representing one, Jake is going to be representing oil and gas. And, I think that we can draw conclusions about the entire industries based on their presentations. So no pressure.
N equals 2 sample size. That seems fair.
Yeah, no, I think that's statistically significant, right? And it's really N equals 1 for each. So seems fine. I don't know. You guys can model that. I don't know. Maybe we can put that in CML and find out if that's legitimate or not. But first, we have to see what the presentations look like. So with that, I will turn it over to Nick to go first. Nicholas, take it away.
Thanks, Michael. So let me go ahead and answer that comment real quick. They are both hand in hand, because if you have worked with jet engines at all, you know that the oil industry is their best friend. So without further ado, we'll hop into this presentation and get cranking. So today we're going to be talking about accelerating AI training using Nvidia GPUs. As Michael said, we're kind of going to be coming at it from two different angles between Jake and myself. Specifically, my presentation and demo is going to be focused on accelerating the actual machine learning training part of it, specifically a neural net, and how huge of speed improvements you can actually get. So we'll just go into it. So just to set the stage a little bit, I'm sure this is a shock to nobody, but the data that's being collected daily globally is increasing like crazy, right? So from 2021 to 2024, global data throughput's expected to nearly double, right? And someone has to do something with this data, right? As I've heard a lot in my previous job, data is useless. Information is what people need, right? So in order for people to turn this data into information, it has to be computed in some way, shape, or form, right? So while computational and hardware power has certainly skyrocketed, right? You're looking at a 250 megabyte hard drive from the late 70s. You can all imagine how large a, well, let's see, right? This is 128 gigabytes right here. It's about the size of my thumbnail, right? So as hardware has clearly gone through the roof, software has kind of tried to follow suit, right? So things that were cutting edge, a couple of decades ago, some like things like linear regression and like stuff like that on computers have transitioned more to things like neural networks and deep learning today, right? So why? What's allowed for these advances? So one of the big things in the past about 20 years or so has been the ability to use different hardware, right? So CPUs have kind of been the traditional way and the traditional piece of hardware that computes many things in a computer, right? The CPU normally has anywhere these days from 8 to 64 cores, right? Whereas GPUs kind of are more recent, right? They came in the early 2000s, really kind of started taking force. And the big difference is that GPUs are more catered to having more cores and more parallelism, right? But less heavy computational power. So each core can do less. But as a result, like a single Nvidia A100 has 6,900 CUDA cores, right? Now, it's not one-to-one, but there's a few kind of things we want to compare, right? So just looking at some quick differences between CPUs and GPUs, I took two kind of consumer examples, right? Something that, and I apologize for anybody listening that's trying to get their hands on a new NVIDIA GPU, but most people should, in a normal world, be able to access either one of these things. On the left is kind of like a mid-grade CPU. It's actually the one that's in my computer. It's a Ryzen 7 3700. And to look at two kind of important performance statistics, right? The theoretical limit for floating point, 32-bit floating point operations is 1.69 teraflops, right? Now, flops just stands for floating point operations per second, tera being the amount of them, right? So that's what this CPU is capable of doing, right? These CPUs will be running on DDR4 RAM, taking the most common one, 3200 megahertz. That bandwidth is about 175 gigabits per second. Now, whether or not those numbers mean anything to you, the important thing here is the comparison. So if we take an Nvidia RTX 3080, which is not the highest end card, but it's the second highest end, right? So let's say mid to high end of the pack, right? You can see that the amount of floating point, 32-bit floating point operations it can do compared to a CPU is something like 30 times, right? And not only that, but the RAM, the memory on this card, has a much higher bandwidth, right? So how does this help us do anything, right? Fortunately for us, since about 2004, there has been a lot of work put in to essentially taking these low-level algorithms that are really used heavily in machine learning and optimizing them for the high parallelism and memory bandwidth you get out of a GPU. So on the left-hand side is a sample of some, not all, of the libraries that have been developed under Cuda, which is NVIDIA's Compute Unified Device Architecture. It really just is the framework where all of these are housed underneath, right? And you'll see it's things like basic linear algebra, fast Fourier transforms for things like signal processing, right? General math libraries, random number libraries, sparse solvers, all these good math low-level functions, right? And on the right-hand side, you see this beautiful diagram that I got off Wikipedia, which is actually I like a lot, except for GeForce 8800 kind of dates it a little bit. But it shows you that in order to leverage all the cores and the higher memory bandwidth of a GPU, right, you swap the data that you need into the GPU's memory, and then the CPU, through these libraries, passes the GPU instructions in telling it how it needs to calculate these. Once the GPU is done, it can grab the results out of memory from the GPU, pull them back into the system memory where you can go and go about whatever you're trying to do. So how do you actually use this, right? Are developers like you or I actually sitting there and implementing these, optimized low-level math functions and doing fast Fourier transforms? Probably not. But fortunately for us, there are a lot of smart people that have dedicated time to abstracting these, right? So now we have higher level libraries like TensorFlow and PyTorch that let normal everyday developers actually leverage all of these optimized math functions, right? So Nvidia GPUs are the hardware, right? Cuda is kind of the framework in general. Something like Cudin, which is what specifically we're going to be using at a low level today. We're not actually going to be so Cudin's going to be running in the background. We're going to be using TensorFlow, but Cudin is a specific library that's speeds up neural net training. And then TensorFlow and Keras are two kind of higher level libraries in Python that allow us to apply all of these things without having to know them at a very, very low level, right? So how are we going to look at this today? We're going to take a neural net, an image classification neural net, arguably the most popular one. That's called ResNet 50. This is a neural net that is trained on a huge repository of classified images. So essentially, its goal is that you could feed it an image, and it has learned off millions and millions of classified images before, and it can tell you with some level of precision what that image is. Is it a tabby cat? Is it a spoon? Is it a hot dog, right? And what we're going to do today, because this model, you can already get it pre-trained, right? So we need to actually train something. So we're going to take another image classification, an open source data set called Sci-Far 10, right? And what we're going to do is we're going to take our original neural net, and we are actually going to freeze all the convolutional layers. Now, we're not going to get too deep into how a neural net works and everything. That's kind of out of the scope of this. But the way you can think of it is that the convolutional layers, especially the deeper layers, they have very, very basic features, right? So it's not trying to figure out if this thing is a cat, right? It's doing some very low level transforms that are trying to figure out, maybe where certain gradients are and where the main object is. Things that are applicable regardless of what image you're looking at. The final layers are the ones that actually go more in depth and try to classify, right? So we're going to chop those dense layers off and we're going to train new ones. Now, again, the point of this is not to come up with some crazy, accurate, awesome model. The point here is that we are retraining a neural net. The reason that is important is because retraining a neural net takes a very long time and it is very computationally expensive. So we're going to show the difference between training the same neural net with the same code on a CPU only machine, 1 GPU, and 2 GPUs. And you're going to see the vast time difference. So we're doing this today in Cloudera machine learning. That's a part of the Cloudera data platform. It will afford us some very nice benefits. The runtime is already preset up for us. What that means basically is that aside from some Python pip installs, everything else is going to be set up for us, meaning that NVIDIA drivers are good to go. The Cuda installation is there. All the files exist and it can all run. That is not necessarily trivial. Having set it up on my personal machine, it is very picky and choosy. So it is really nice to have that set up for us. It also lets us do cool things like security and governance. So for example, Jake and I are actually on the same instance of Cloudera machine learning, but neither one of us can see each other's projects. And that's like that on purpose. If I wanted to share it with him, I could, and vice versa. But we can actually still operate in the same place. And depending on who gets access to what, we can kind of jump back and forth. So it's pretty cool. And without further ado, I will actually just bring us in to the Cloudera data platform. This is kind of like the home page. So the Cloudera data platform does a lot more than just machine learning, but we're not looking at any of that today. We're just specifically focused on the machine learning part. So we're going to go into the machine learning experience. We're going to go into a workspace. This just lets us define how many resources and what kind of resources we want. So now we're into the projects page. So the projects just let you set up and kind of compartmentalize different things that you may be working on. Right now, I only have one, and it's transfer learning on GPUs. So let's go ahead and go into it. So the first thing you'll see is there are 4 files in here, right? There is a CDSW build shell file. That's not important to us right now. Main.py is where the most of our code, all of our code is. We're going to look at that in a second. We've got a README that just gives you, this is actually the README right here. It just gives you a really quick overlook of what is in this code and what it does, and any important things you may need to know. And then a requirements.txt file. If you're, familiar with Python, this is just going to house the packages that we are currently using. You'll see it's a pretty light lift. We just have Keras and Tensorflow. We specify the versions because it's pretty important. So I'm going to show and walk through the code that we're going to run and just talk about what's going on so that we can understand where the magic of TensorFlow really is and why it's speeding it up so much and how much it's actually speeding it up. So let's go and so this is all just legal stuff. Sorry, this is kind of lagging a little bit. There we go. We got our imports. Nothing crazy here. In fact, you'll see that there's very few imports, which is, in my opinion, very nice, right? We just need to import TensorFlow, Keras, some operating system. Time and date time is just so that we can track how long this thing actually takes, all right? And CDSW is actually letting us make use of what we call experiments, which really just gives us a nice UI in which to run our code. And we'll kind of go into more of that when we run it. So this part, we just needed to copy one file over. Again, Cudin is very finicky, and it is very hard to match the exact versions. That is a fun game to play. Fortunately, we only had to do this one little thing, and it was working great after that. This is just telling us how many GPUs we have available to us. This is just important to know because a lot of times the code, especially the way that this code is written, is very malleable in the sense that it will run just fine on CPUs, right? So it's nice to know at the beginning what you're actually running this on, right? And that way, when something takes a long time, you know why. So now we're going to go into what's actually going to train the model. We're bringing in our data set. Fortunately, Keras, being the kind of high-level API for TensorFlow, has some data sets available, so we can pull the SciFar data set in without, any kind of hassles. It's really nice. We're splitting it into test and train sets, like you would with most machine learning processes here. We're defining the shape. In this case, we're telling it that we're going to feed it 32 by 32 pixel images. 3 is the alpha layers, so there's a RGB layer for each image. So the input shape is 32, 32, 3. Now here is actually where the big magic comes in. So we are going to be doing what's called a mirrored strategy, right? TF is TensorFlow, so we're just telling TensorFlow that when you're going to train this model, train it and distribute the load using a mirrored strategy. So now when we do a mirrored strategy.scope, anything that is in that scope, when it is called, it gets automatically routed to either however many CPUs you have, or if you have GPUs available, it'll route it to the GPU. And even as a bonus, if you have multiple GPUs available, it will figure out how to split the load up between those GPUs, right? So it's super powerful. So the first thing we're going to do within the scope is we're going to bring in the ResNet pre-trained model, right? We're going to include top means we're not going to take that top layer because we're going to create our own. The weights are going to be the default ImageNet weights, and the input tensor is what we have defined here so that it matches what we are going to be feeding it, right? So then, as in the previous diagram, we are freezing all of the early layers, right? So if you see, for layer up from 0 to 143, we're not making these trainable, so we are freezing them all. Then we are creating the last batch of layers. This is going to be kind of what does the final image classification. Note here, this is not by any stretch of the imagination the most or best way to do this possible. This is just a way. So I don't want to, say that this is the end-all, be-all, best neural net that you can possibly make here. So I just want to put that disclaimer out there. We're going to make a checkpoint. This is just kind of part of the neural net training process. It's basically telling it what to try to maximize, right? And if you're saving only the best model, what to save the model as. Then it's compiling the model. And now here's really the meat of it, right? So when we train the model, we are going to start a timer where you're going to train the model, and we are going to end the timer, right? So the only part that we are keeping track of, really the only part that takes any amount of time in this code, is this model training, right? So this is what we're going to be outputting, right? Now, the very end, what we're doing here, right, is we're just taking the amount of train time and we are outputting it to a tracked metric. This is something in Cloudera machine learning that just makes it so that we can run this code and the UI will spit back a result. So before I go over to the experiments, I have a question for chat. I have run this already on the CPU, and the reason that I have already run this on a CPU is because this meetup is only so long. So I will tell you beforehand. Actually, we'll just go. Okay, no, I want to ask it. So the CPU run took 111 minutes to run. I've also run the 1 GPU just because I wanted to get that one done out of the way, and we're going to run the 2 GPU today. But I want everyone to guess, before I show you the number, if the CPU model took 1 hour and 1 hour and 51 minutes, I believe, to run, how long do you think 1 GPU took? And I'll give you 20 seconds before I go over the page that's going to unfortunately spoil the answer for us. Yeah, 20 seconds is a long time for dead air, but I want to at least get some. Yeah. Okay, we're going to ruin the answer for you. So we're going to go into experiments. Experiments gives us a nice UI to actually run kind of compartmentalized code in. And you'll see that, it was 112 minutes, not an hour and 50. I'm sorry. So you'll see that the CPU took, what was an hour and 50? I'm sorry, 112 minutes is an hour and 50 minutes. So you'll see it took an hour and 50 minutes for a CPU only run. One GPU took 5 minutes and 3 seconds. And we're going to run this one more time so you know that this isn't bogus. So main.py is the script that we just ran. We're going to run it on Python 3.8. Again, this is kind of CML saving us the time, CML being Cloudera machine learning. We get to just choose Nvidia GPU as the addition, and it kind of does a bunch of stuff for us. We're going to give it 4 cores of CPU, 32 gigs of memory. By the way, all other runs were with the exact same resource profile, right? We're not cheating and throwing a bunch more CPU and RAM at the other one. And this time we are going to run it on 2 GPUs, right? We're going to leave ourselves a comment just so we know. And we're going to start the run. So this is actually pretty cool. So now that we've started this, right, it is now building its own runtime, right? And the cool part is that you could run a bunch of these experiments at the same time, and it'll do individual resources for each. And so especially for something like this, where you're trying to compare how long different models train, in a previous exercise, basically, there's another tweak, another knob in neural nets, right? And that is actually called the batch size. Batch size is basically telling it how many things you're feeding each instruction set at once. And that is heavily dependent on your actual hardware, right? So if you have 4 GPUs, let's say, you can use a much larger batch size than if you only had 1. So I use experiments to actually put in a bunch of different batch sizes to see what worked, what stuck, what didn't work. And at the same time, since I can track metrics, it would spit out the results right here for whatever I wanted. So it's really nice to track everything in one place. On top of that, when you actually run something, you can watch it go, right? So it's building right now. I just need to give it a second to go. It is pushing. As soon as it starts going, you'll see that it'll log the output for you. So you can actually watch it as it trains. It should only be a couple more seconds now. And again, this is a pretty light training set, all things considered. It's not a huge data set, and we're only training the final layers, right? So if you wanted to build a neural net from scratch and train everything, right, it is going to take a lot more time than this, right? Now, that's not to say you can't throw more resources at it or optimize it more, but the idea here is that if you were stuck without these kinds of advancements, right, if you were stuck on CPU only, or maybe just where you're at, for example, my previous job, I really didn't have access to GPUs, right? Like the machines that we were on were workstations that were maybe 6-7 years old, and originally when they planned and spec'd out the rack server we ended up finally getting, well, they weren't taking into account that we would want to actually run these things, and as a result, we really were running into time issues, in the sense that the fleets depended on us daily, right? We would give them daily reports on what's good, what's bad, etc. And that process to bring in and process all that data had to run overnight, right? It had to finish between the time that we left and the time that we came back. Otherwise, we wouldn't have a report to deliver in the morning. And when we first designed it, the process took maybe 4 hours, right? A year later, that process was taking 8 hours, right? And at that point, we had to start figuring out, well, the data's not getting smaller, right? How do we keep up? And that's when we start expanding into that distributed computing land. And I will tell you that not having access to GPUs was actually a huge downside, right? It was a big loss. So fortunately, cloud resources being as abundant as they are, it's really, really easy to spool up as many GPUs as you need to in something like Cloudera machine learning. Sure. So while we're waiting for this to spool up, again, we have a raffle. So now is the best time, as good a time as any, to get some questions in the chat. I will do my best to answer them right now. I do see some guesses. We got 10 minutes, 20 minutes. Doesn't look like anybody guessed 5. So I think because I haven't ran anything in a little while, it's taking a little bit to schedule, which is unfortunate. But why don't we come back to it? We'll let Jake do his demo, and then we can come and we can look at the results at the end of it.
Thanks, Nick. Yeah, really interesting stuff. Really enjoyed watching that and be anxious to see how it turns out there at the end. So go ahead and hop right into mine. I'm going to kick off my CPU job to start. I'm going to present, and then I'm going to try to run the GPU live. And so as with any live demo, fingers crossed everything goes well. But I'm just in Cloudera machine learning here right now. I'm going to go into this taxi fare prediction project. All I'm doing in this project basically is trying to do a pretty standard, I think a lot of people have played with this data, just predict taxi fares in New York City. New York City has a lot of great open data. And so in Cloudera machine learning, normally what I do, I go in and I start up a session to get myself some resources and to start developing. While Nick probably wasn't really demoing this, but I'm actually going to be using Jupyter Lab. One of the great things about CML is you can bring different editors, right? You can use the native workbench or you can use Jupyter Lab. I'm going to use the Rapids runtime. That's going to give me, and I'm going to talk about what Rapids is today. And as well, so you can see the resource I'm giving this is 4 CPUs, 32 gigs of memory, and also attaching a GPU. Just like Nick said, pretty amazing if anyone has messed around trying to work with GPUs on a machine by themselves. A lot of hassle involved in that. This is just super nice to be able to spin stuff up and use it. I already have one running. So we're going to go ahead and open that up right now. And yes, everything is still up and running. And I'm going to go ahead and run this. And we're going to come back and we will talk about it in a second. Let's make sure it's going. Yep, we are running. Okay. So let's go ahead and present this. So some of the challenges, Nick has already alluded to that. I think kind of he just ended with one of the challenges that we see a lot today that everyone runs into is that data science work is more and more time consuming. Really as time goes on, talking about, we always talk about the explosion of data and where things are going. But a lot of times the work of data scientists is just constrained by the slow compute. And so a lot of times a pattern that we see people doing is that, I have to get this done today. I need to just get a working version of it. So I will downsample my data just so I can make progress faster. Another issue that we see with all the big data there is that it's becoming more and more costly to do data science. So if you're working on like a really large scale CPU infrastructure, it can become super expensive to be able to process all that data across the CPU infrastructure you would need in order to process terabytes worth of data. And the last thing is sometimes things have become a little unreliable, right? If you're working in the open source world, some of those libraries you're working with, you have one version of this, one version of another, and it just becomes a little hard to keep track of everything and know that it's all going to work and that it's reproducible. When I go to demo it in front of my boss or say in a live stream, is it all going to work? Can I rely on that? This is a really neat graphic that I like because it's kind of a little bit of a humorous representation, but those that have worked in data science are all too familiar with this. On the left, we see kind of the CPU-powered workflow that people might be familiar with. You get in at 9 o'clock here. You configure your ETL workflow for like an hour, and then you go ahead and start that to get your data ready. You go get a coffee. You come back and check it. It's still running. Maybe you check some emails. You go out and get another coffee. You get another coffee. And then you go, and by the time you get back, you notice, oh man, something went wrong. Crap, I forgot to add a feature. So I go back, restart the ETL workflow, go switch to decaf as it shows. You're still waiting, and then finally, oh man, there were some null values that weren't expected at this part of the ETL script. And so I reconfigure and then I run it again, and then I'm gonna have to stay late so I can see that this is actually gonna end up working, and all of a sudden it's past 6 o'clock. So that's something that I think we've all been there and have all experienced when you get to a certain level of data. So the idea of GPU workflow is really about the speed, right? So if I can configure my ETL workflow I can start that ETL workflow then, and maybe I'll run and get a coffee real quick. Like by the time I get back, it's done. And then, I did forget to add a feature. Then I can make that change, get that done quick. And you just get more and more time to iterate. And there really is just so much value in that ability to iterate. Something that we always talk about, in data science, a lot of times, depending on the scale that you're working at, even like a minuscule improvement in your accuracy can mean millions and millions of dollars because you're providing that prediction for thousands and thousands of customers. So something that's really important to keep in mind is that, even though the models from GPUs might not be more accurate if they come from GPUs or CPUs, but just the fact that you can iterate over the same thing quicker and quicker gives you an advantage. So here's the data workflows within NVIDIA and kind of how they approach the overall data science process. So NVIDIA accelerates two different ecosystems. One is the Apache Spark ecosystem. I think many of you are familiar with, and then as well as just the overall PyData ecosystem. A lot of what Cloudera has been talking about recently is how we're speeding up Apache Spark and how easy it is to implement that and how low code change it is once you have it implemented. But there's all these other improvements that are being made in the entire PyData ecosystem with Rapids AI. And that's kind of a little bit more what I'm going to be talking about today is that Rapids AI. For Cloudera, we have different form factors depending if you're on-prem or if you're in the cloud. We're the hybrid data cloud company. And so if you see here, we have the PBC base or experiences for Cloudera data platform. But today we're really going to be focusing on and using stuff in the public cloud. So down there in the cloud base. And that spans the entire data science end-to-end process. So what is NVIDIA Rapids, you might say? For starters, it's all about open GPU data science. It's open source libraries to execute data science on GPUs. It's not behind a paywall. In something that is open to you, you can pip install it and work with it. Under the hood, it is Cuda. And so what Nick was talking about demonstrating, you are still using Cuda. But the nice thing is that it's Cuda, but with an abstraction above it with a familiar syntax. And so if you're familiar with scikit-learn, if you're familiar with pandas and those kind of common data science libraries, you're going to be super familiar working with these Rapids libraries. The last thing is that it also scales out to production workloads. So while it improves work on a single GPU, it also enables you to work onto clustered GPUs. So if you have too much data to fit onto one GPU, you can scale it out beyond. And so to dig into that just a little bit more specific, I made some references there to pandas and scikit-learn. So in the worlds of Rapids, we have some libraries. We have cuDF, we have cuML, and we have cuGraph. So for cuDF, that is synonymous to pandas. QML is synonymous to scikit-learn. And we have cuGraph, which I think is Network X. It's much familiar in Python. And so when I say is similar, I mean super similar. So I remember when I was going to work with PySpark for the first time and someone was like, oh, and it wasn't the first time, but later on when PySpark became more popular and they had data frames come out and everyone kind of said it's like working with a pandas data frame, but you're working in Spark, and you go and you try to work the exact same way, and you quickly find out yeah, it's similar, but there's some pretty key differences, and you make a few mistakes along the way. So it's not exactly one-to-one in that situation. In this, it is really almost one-to-one, and some that's really neat. And it's the same for QML with scikit-learn. And so that's really today what I want to demonstrate and show you guys is how easy it is if you are a data scientist that is really comfortable with pandas and you're really comfortable with scikit-learn, something like I was, and you're a little nervous about I saw that code that Nick wrote. Maybe it's a little complex and I kind of want to stay in my comfort zone. Rapids really removes those barriers of entry for you to be able to go and work with the syntax that you're super familiar with. In fact, you could instead of importing pandas as PD, you could import cuDF as PD and basically get and do the exact same thing. And that's what I'm going to be showing you today. And last thing, so I'm going to be demonstrating some of these speedups in real time, but this is just some benchmarks that NVIDIA has done. So if you look on the y-axis here, we have the CPU nodes. So as it goes down, you have 20 CPU nodes, 30 CPU nodes, 50, 100, and then just 16 GPUs. So we have it broken into the load and preparing data step. We have an ML training step with XGBoost, and then just the overall end-to-end performance of them combined. So you can see, even compared to a 100 CPU node cluster, working with GPUs, you can get much faster times. So something that's really, like, I think everyone has always known, like, yeah, if I work with GPUs, it's going to go a lot faster, but it might be a little intimidating to make that switch and work with it. And so as I kind of showed there, last thing I want to say is that we've integrated the into our runtimes, the Rapids accelerated GPUs, to make it really easy for you to get up and running with the Rapids libraries. You don't have to worry about, did I install the NVIDIA drivers properly on all these different nodes? Like, we've removed that from you in this situation in the public cloud. Let's go ahead and fingers crossed that we have no errors so far, and just see if we are. So we still have our script is running a little bit here. So I'm going to dig in and explain some of the code, and we can see what I did. So at the very beginning here, you can see that I've set my mode to run in CPU right now. That's just for convenience. So because I really want to demonstrate to you guys like that switching between CPU and GPUs. So if you look at my import statements, if mode is CPU, I have your import statements that you've always seen. Import pandas as PD, import numpy as NP, the sklearn libraries, pretty common stuff. However, if I set this to GPU, I'm going to do those import statements similar, but I'm going to import cuDF as PD. I'm going to import QPy as NP. I'm going to import the different sklearn libraries as QML and do the train test splits. All those kind of so it's going to have to work the exact same with the exact same syntax. And I found like a couple of areas where it's a little bit different, and I split those out with if statements, so we can take a look at that so that you can understand them. So what am I doing in here? I'm trying to predict how much it's going to cost to take a taxi in New York City. I'm working with not a ton of data. I just grabbed a couple months worth of data from 2015. I was trying to find that sweet spot of like the amount of data that can still fit onto one GPU, but is large enough to where I'm like just right there, so I can show the speed performance in ways that's not like, hey, look, instead of taking 10 seconds, this took half a second. That's not as neat of a demonstration in my mind. And so if we look at the, so that's before I've already imported the taxi data. We're going through a data prep step where I'm bringing in data. This is one of the spots that I found that there is a little bit of difference between pandas and cuDF, in that with cuDF, they have a neat way when you're doing your data types that you can actually pass in a data type, and it handles dates super well. Whereas with pandas, you had to pass in that data type as just a string, and then you would parse those dates with the parse dates attribute. And so that's one difference where it was just a little bit different, and there's maybe ways and you could do it in which it would be the exact same, but that's one of the only places that I found a difference in. And in my opinion, like, dates are always hard to work with in times. I always end up Googling a bunch to remember how to do things. So we go through that. We have two different CSVs that we're just grabbing and we're putting them together. It's in the data here. In NYC taxi data, we have 2 months. So you can see we have January and February in 2015. And it comes out to a data set of, let's see, 25 million rows. So pretty decent data set. And you can see some of the attributes here. We have like a pickup time, a drop-off time. We have the passenger count, the distance of the trip, lat long, et cetera, things that we could work with. So then I went through and did some just pretty common data cleaning stuff that you might want to do. For one, we want to just like standardize the names of the columns. I did some exploratory data analysis, just did some graphing and found like there was some outlier data. For example, like we had some passenger counts that were quite large, and I felt like that kind of threw off what we're trying to get at for the average taxi. We had some trip distances in New York that were over 500. Also, if you looked at the lat long plots for that, it really wasn't realistic for that being in New York. And sometimes too, we had somewhere I don't know if people were taking submarines into the middle of the ocean. So that was a little different too. So I figured that out. So, and for all of these, I just did a quick time just to check how long it's taking. Even on CPUs, these are pretty fast steps, right? It's taking 4 seconds. It's taking 5 seconds to do these. I do some one-hot encoding for some of those categorical type features because I need to do that for my model to be able to interpret them properly. I do some time features, something that's pretty common to do if you have a date. There's a lot of interesting information you get out of there, right? If you think about just the hour, the month, the day of the week, is it a weekend or is it not a weekend. Things that I would just think would be very influential for a model for predicting cab fares. And then here's the one that I really want to stress at that ended up being a big difference in the amount of time it takes to run. So there's a Haversine distance. And what a Haversine, I've heard it pronounced different ways. But what that is basically calculating the distance between 2 points, but taking into account the curvature of the Earth. Not really, like, normally I wouldn't do this for just New York because that's not really like that big of a deal. They're not traveling that far. The curvature isn't there. But what I really wanted to do is use and see how does a user-defined function work in CPUs versus GPUs with like pandas versus Cuda. And that is the one area. All these others are exactly the same. So everything you've seen when I'm running in CPUs, right? It's the exact same when you run it in GPUs. Nothing changes in doing these things, in doing the get dummies, and doing the filters. All that is exactly the same. However, when I'm doing a user-defined function, there are some differences. So I wasn't able to do that exactly the same. If you can see here in CPU, I'm defining my function, and then I'm just doing applying that and using a lambda to apply to each row. When I did it with the GPUs, it was a little tricky. I had to like do this enumerate and zip to be able to iterate through each row, and really because it is still kind of like parallelizing that, right? So in pandas, I'm still on a single core when I'm doing that, and here, kind of what Nick was referring to is that work is being distributed kind of across all those cores within GPU. So it becomes a little bit harder to do those user-defined functions, but also becomes super beneficial. So if you just look at the wall time for this was 8 minutes and 40 seconds to do this user-defined function. That's always been my experience, is that I get really good performance in pandas for the most of the time, but whenever I want to do something that's a little bit weird outside of the box and I'm using a user-defined function, it's a little bit hard to do. So at the end, I have this final data set. It is 23 million rows. You can see what it looks like here. And then I go through just a pretty straightforward, I'm going to train just a linear regression model on it and predict it. And so you can see I get really good prediction out of my model. I just did a train test split where I took out 20% of the data, held that out. Maybe if I want to do something a little bit better, I could do some cross-validation. But just gives you a good idea of that I am getting very good accuracy out of this data that I put together. And it makes sense. Like if I knew how long a trip was going to take, I knew how long it was going to be, I knew how many people were in it, you would think you'd be able to predict pretty accurately how long a taxi ride is going to take. And then I pick that model and save it. And you can see, so this all took me 12 minutes and 16 seconds. Not a super long time, but one of those instances where if I was working with a lot of data, I would need a lot of RAM. And then also working more data, you'd have to go away and wait to see what happened. And then if something, messed up at the end, like crap, I have to restart. And waiting around 12 minutes, it's not my favorite thing to do. So let's rerun this again now with GPUs. So again, I just want to point out, all I'm doing now is I'm going to import cuDF SPD. I'm going to import QPy as MP, QML. I'm using different libraries, but the syntax remains exactly the same, except for those 2 points that I pointed out. So if we do, we're going to restart the kernel, and we're going to run all the cells. Restart, run all cells, and let's see how long it takes. And one of the big ones I want to see is how long this user-defined function takes. Oh, it's already went by it. So that took, instead of 8 minutes, that took 470 milliseconds. So that whole, oh, we're already done. So we went from about 12 minutes, we took that down to 10 seconds. My syntax, except for 2 real outlier situations, remained exactly the same. So that's really like the value proposition to me. I came into, 5 months ago, I had never worked with GPUs before. I very quickly, like in a matter of days, was able to get up and running in Rapids and work with GPUs very easily in a way that it's not intimidating, it's easy, it's familiar for me to do. And that's really the value that is brought with working with those Rapids libraries. And let's maybe turn back to Nick and see if see where he's at with his script.
Cool. That was honestly, that was really cool. So I mean, the fact that you're going from minutes to seconds, right? That really is like totally game changing, right? So I have some very interesting results that I did not expect, but I think I understand why, and I think hopefully everyone can learn along with me here. So when I have run this experiment in the past, last week and the week before, we used much smaller GPUs than we have used this time around, right? The reasoning being that we wanted to wow, an audience, right? We wanted to show you guys just how much faster it really could be. So in previous attempts at this, we were using Nvidia Tesla K80s, which are kind of close to that 3080 that I showed in the presentation as far as bandwidth goes. Well, today we upgraded to the big boys, and we were running this on V100s. So if you have a keen eye, you'll notice that the 2 GPU experiment actually took a minute longer. That is not a result that I expected, but I suspect that this is actually because the data set we are feeding it is not actually large enough to matter. It would have ran just fine on one single V100, and therefore throwing it at 2 just increased our overhead and actually decreased our performance. So in previous attempts, the training time for CPU was about the same, but the training time for one GPU was 13 minutes and 2 GPUs was 7 minutes, right? A nice kind of linear, twice as fast scale. Well, what I'm learning here is that the size of your data set and the size of GPU you actually need correlates. So if you are fortunate enough to have 2 V100s at your disposal, you might not need them for every training data set. Now, where are we getting these? I think that's an important part that I didn't touch on. I'm not sure if Jake really touched on it too much either, but since we are running this on the public cloud, what we're actually leveraging are cloud resources, right? We don't have 2 V100s just, sitting in, Cloudera offices, or do we? I'm not sure. I don't think so. But AWS sure has a lot of them, right? So we are essentially just borrowing from them. We are spooling them up. We are linking to those resources. We are using them. And as soon as this experiment is done, we are letting them go. So we are just paying for the compute time we're using. So it's actually really, really nice from a cost standpoint and an availability standpoint. If anyone else has tried to get their hands on any recent GPUs, you know exactly what I mean. So with that being said, there are a bunch of good questions in chat. I will pass it back over to our gracious host to moderate the Q&A.
Oh, sorry about that. Thank you so much, Nick. It is funny how sometimes you can sort of over optimize, or you can kind of false optimizations. I remember years ago doing a consulting engagement at a customer prospect, and they were comparing Impala to Microsoft SQL Server, and SQL Server was faster, but the thing was they only had like 10 gigabytes of data, and it was like, well, yeah, I mean, the overhead of spinning up a distributed computing MPP database is almost always going to be significantly higher than if you could just put it in memory on a single node, and so it's, it really depends, like you said, there's going to be overhead in parallelizing anything, and then if you don't need to, if the data set is so small that it could fit in one, then you don't get a benefit. All right, so we do have some questions. Just scrolling through. One of them from Jeff asks, is AMD working on anything to compete with or be compatible with Nvidia Cuda? So the answer that I know is that in AMD land, the sort of equivalent thing to Cuda would be OpenCL. However, I don't know that there is much in terms of third-party library support for that. I know I saw that Google released like TensorFlow Lite running on AMD, but it's for like Android devices. So I don't know if Nick or Jake has more information about that.
Yeah, so there was a big open source push, and there kind of has been a little bit, not just for AMD, but actually Apple was pretty involved in it as well, considering they have their own chipset, right? But what it comes down to is really just adoption. So, like, pretty much anybody currently that's making open source libraries or using open source libraries, since CUDA has been so embraced for such a long time, it's just become the de facto go-to. So, if anyone is developing some kind of more efficient algorithm for some, linear algebra solver or something, they're going to make sure it works on CUDA first. And then if it works on OpenCL, then great. But I haven't seen much support as far as actually using it. So unfortunately, what that means is you're kind of stuck to Nvidia GPUs. And I am not being paid nor sponsored by Nvidia, though. If they're listening, I would love to take sponsorships. So.
Well, I will say that Cloudera has a great working partnership with Nvidia, and we have jointly certified solutions, and we can leverage their cloud resources. So, and we've even worked together on getting some GPU support in Spark 3 for data engineering. So, certainly, Cloudera has a strong relationship with Nvidia. Having said that, I'm sure if the market changed overnight and there was a bunch of machine learning technology built on AMD, we would we would be able to leverage that as well. But yeah, the Nvidia kind of won the AI ML market years ago, and that's kind of where it is. All right, let's see. There's another question. Which GPU is this being run on? And I think we kind of answered it, but 3080, 3090, special AI card, Magic Fairy Dust.
So yeah,
Magic Fairy Dust.
Reverse engineered alien technology. Tell us more.
It is Magic Fairy Dust, which is basically the same thing as a new 30 series card, right? As far as being able to obtain it. So yeah, this is being run on V100s. And again, you can kind of specify that. So previously had run on smaller GPUs. In this case, we wanted to go, with the big boys. So yeah, these are running on 1 or 2 V100s.
I think, Nick, one of the things that may have prompted this question is in your slides, you showed a 3080. Now, I know you have a super fancy GPU on your home workstation, and I think one of the benefits might be I think you were doing some prototyping in that environment, and then the benefit of sort of the Cloudera environment is you can sort of migrate from there to the data center, to the public cloud, private cloud, wherever you need to run it.
Yeah, and it's true. And the actual cool part is that as far as writing TensorFlow goes, the exact code that worked on my home station worked on this instance of CML. So it was really just like plug and play, right? I could develop here, I could develop on the cloud, right? And that's kind of like the whole hybrid workflow that everyone's kind of been talking about, which is that I can write the same code, run it on-prem, and take that code and be like, oh, well, my GPU might not keep up, or my data set is massive, so I can just upload it. I can borrow 4 V100s from AWS for, 10 minutes, and I can get all of my training done and get my model back and save it and run from there instead of waiting a couple hours for my home station to do it.
Yeah, absolutely. And there was a comment in the chat about how the V100s are expensive, and that's where the benefit of cloud infrastructure comes into play, because for something like this, you may not need access to a V100 24/7, but it may benefit significantly on certain jobs for a certain short period of time, so you can sort of pay for that as an operational expense as you use it, rather than having a sunk cost in capex like you would do with a traditional data center. Let's see. So Jake, here's one for you. Did Jake say he was using the Rapids software library? So I know you definitely did say that. I don't know if there's anything that you want to elaborate.
Yeah, I was using QDF and QML were the 2 main Rapids libraries that I was using, and then there was a couple more that you can work with, but those are the main 2 that I was focused on using.
Yeah, and then I think, Jake, this might be, I guess it's a question for both, but we'll just say for you. Question is this distributed CUDA or running on a single machine?
Mine was running on a single machine, so I was running on just a single GPU. There is ways. So if I had gotten into and gone past a couple months worth of data, start working with like 3-4 months worth of data, there is integration between the Rapids libraries and Dask, in which I could scale that out amongst multiple GPUs to be able to get that parallelism if I wanted to do that. So I could scale out. But for this instance, I wanted to keep it like very straightforward. When you start working with Dask, it gets a little bit more hairy, and I probably wouldn't be able to do those exact switches between like QDF and pandas. And that's really what I wanted to demonstrate in this situation. If you were working on like a single machine and you wanted to get those speed ups.
Yeah, it makes sense. Okay, so there's another question. Can you use NVIDIA GPUs for Spark? The answer is yes. I don't know, Nick or Jake, if you can speak to that, because see, from a Cloudera perspective, we would think of that probably more as a data engineering task. At least that's when we think about the work that NVIDIA has done in Spark 3. That's kind of where we see it, but there may be some machine learning aspects to it as well. I don't know.
Well, yeah, so the Rapids Accelerator for Apache Spark is for Spark 3 specifically, and it accelerates specific parts of Spark. So it's not everything in Spark, right? Certain of the APIs work with that, and then certain of them don't. So the ones that do work are like data frames, and what was it? There's another, but I know for sure like Spark ML, that's not working with it. And so it is really nice to work with. So you can work with GPUs in Spark, and the way that it's implemented lower down in Spark. And so that as long as you're working with data frames, any of the shuffles and stuff that's occurring, all that happens in the GPUs, and you don't have to make any changes to your code. All that happens is that the Catalyst optimizer, when it's making the plan to execute it, it says like, can this run faster on a GPU? Yes, it'll run on a GPU. If not, it's going to run on CPU, and you still get that visibility in the DAG afterwards to see, how it runs. So really, we're seeing a lot of success with that with our partners at Cloudera. So like the IRS for one, that is one that we've talked about, where they've implemented GPUs into their Spark workloads, and they're getting, at first it was like 4 to 6 times improvements right away, but now it's all the way up into, I think, like over like 60x improvements. And so it's crazy, the processing improvements that they're seeing.
Yeah, there's actually a blog that I was just reading earlier today, in fact, from Cloudera talking about that. So if you search on our blog site for like IRS GPUs, I think you'd probably find it. And I think actually we linked to a video, Nick, that you had produced, kind of showing some of that in action, if I'm not mistaken.
Yeah, I'll put it in chat in just 1 second here.
Okay, perfect. All right, so great. So good answers there. Let's see. So several people. Well, so Jeff is asking if he should be really happy about the 3080 that he has.
Yes.
And I feel like yes.
Yes, Jeff, you should be extremely happy about that 3080. There are a lot of people that would love to be in your shoes.
Exactly. So Jeff,
what's your address, Jeff? Just want to write that down.
Well, I'm going to flip that a different way. I'm going to say it sounds like Jeff can name his price if he wants to, if he's looking to downgrade his performance a little bit, but increase his bankroll. And then to that end, look, Cloudera making connections, bringing people together. Edward says, well, have them send me a 3080, please. So I don't know, Edward, that we can get NVIDIA to send you a 3080. Now, you're entered into the raffle, but the prizes for that are not NVIDIA GPUs. Unfortunately, our budget is not sufficient to cover that. But I have it on good authority that Jeff Cross may have one for sale. So you guys just, you kind of figure it out, and we'll just take a finder's fee. All right, JW wants to know, will we be able to access a recording/replay of this? And the answer is yes. I believe that all of these get uploaded to our YouTube channel. Does anyone know if that is true or if I just made that up?
That is definitely true. And you can also even find more videos kind of similar if you go to cloudera.com/users. Should I put that in chat too?
Yeah, that is a good call to action, and we will be repeating it in a moment because that is where we want everyone to go for all of this great sort of user marketing, technical marketing content that we have, where we try to, I like to think of it as reality-based marketing, right? Like we actually show the product and what it can do, and we try to hopefully accelerate your use of our products and just, of the engines that we support and all that. Great. Well, I don't see any more questions. So I do see that Edward and Jeff are negotiating. Looks like Jeff's got him up to he's got him up to about 2,500. I think you could go higher, Jeff. I don't know. I mean, Edward seems like he really wants it. Anyway,
get some Bitcoin maybe, or
exactly. Yeah, do it with This sounds like all
some Dogecoin. I'll pay you in Dogecoin.
Yeah,
a lot of Doge.
This definitely sounds like all very official Cloudera supported things. Okay, well, we will wrap the Q&A there, and moving on, as we were just discussing. We do have some resources for you to peruse after the meetup. Obviously, there's a lot of information, very dense, and not everything can be covered, even in the time that we had, and even with those great presentations. So these are kind of 24/7 resources that are available to you. The cloudera.com/users that Nick mentioned is your one-stop shopping for all of the collateral that comes out of our group. And then we also have the video tours. And again, just to remind you, if you don't know where you are, I mean, if you don't know where you are in the real world, maybe call 911. But if you don't know where you are in terms of like the internet and what you're watching, this is the Future of Data Meetup, Northern Virginia chapter. And you can learn more about us at meetup.com/futureofdata-nova. I know sometimes we stream on different platforms. I know I've definitely had that where, something pops up from LinkedIn and I don't know, I just go to my phone. I'm not even trying to unlock it. It sees my face. Suddenly I'm watching some presentation. I don't know what it is. That's where you are. So if that happened to you, that's where you are. All right. Now, post meetup surveys. Some participants may receive a survey, and we would love your participation. It helps us improve and tailor content that is resonates with our attendees and give you what you want and help us kind of get the message out. Now, the moment that we've all been waiting for. I know you guys, you come for the raffle, you stay for the content, but it is raffle time. And so we are now going to do our prize drawing. We have 2 prizes. And just so everyone is aware of how this works, if your name is called, if I call your name, if your name wins, then what you need to do is email your contact information to socialmedia@cloudera.com, because these are real life fabulous prize packs. And so we have to actually mail it to you in the real world. So socialmedia@cloudera.com, one word, is where you will go if you win. So with that, Nick, I believe, is playing Vanna White today. Nick, if you would be so kind as to spin the wheel. Wheel of names. I don't know. Oh, wow. That was a close one. All right, Jeff, I'm really glad that it popped that up, because I was like, holy crap, which one is it on? I don't even know. All right. Anyway, Jeff Cross, winner number 1. Remember, socialmedia@cloudera.com. Email us with your contact information, and we will get you your fabulous prize package. Nick, if you would be so kind as to spin the wheel again. Winner number 2, Osvaldo Perez. Osvaldo, congratulations. You also get a fabulous prize pack. The instructions for you are the same as they were for Jeff. You need to email socialmedia@cloudera.com. That is how you will get your amazing prize pack of Cloudera swag that you can wear with pride and excitement. So this is going to conclude our meetup for the evening. On behalf of the team, I'd like to thank everyone for coming out and helping make such a great event. We can't really do it without participation and without your great questions. And so, really, really appreciate that. And we look forward to seeing you at the next Future of Data meetup. Thanks again for joining us, and have a good night.